downloading a number generator, or at least opening up a number generator today. So when we get to that, I'll tell you what it is, and we'll get out your Chromebooks and all that good business, but not until then. We're talking about simulations and experimental probability and theoretical probability. So your homework is actually going to be on, it's page 782 today, and you're going to do numbers 1 through 10 all. It doesn't sound like much, but they have parts A, B, and C. You will be able to probably get it done by the time you go home today if you actually decide to work. If you decide to visit and chill and be playing on the Chromebooks instead of actually using them the way you're supposed to, you're going to have homework, okay? So do the right thing today and get your math done. Now, there are two different types of probability, experimental and theoretical. Anybody think they have an idea which one's which? What do you think experimental would mean? You're actually going to do it. You're going to try it. You're going to figure out how to make that happen, okay? And then theoretical, in theory. So in other words, it seems like common sense would work in theoretical probability. Oftentimes those numbers, when you figure them out, they'll be very, very close to the truth. But sometimes they might be a little bit off. Like if you were to take a penny, there's a heads and a tails, right? If you only flipped it 2 times, you might get nothing but heads on those 2 times. But that really wouldn't be an accurate descriptor of what could have happened, right? So sometimes you might have to do 100 tries. The more tries you do in an experiment, usually the closer you get to being accurate in theory as well. So the more you do it, the closer it comes to what you expected it to be in most cases, okay? And that's where the number generator is going to be helpful to you today. So let's figure out what's going on here. So we're going to figure out what the experimental probability is, and then we're going to move on to theoretical and experimental at the same time. Example 1 says, Matt recorded that it rained 8 times in November and it snowed 3 times. All the other days it was sunny. There are 30 days in November. Find the experimental probability that a day in November is sunny. So when you do probability, it's what you want to happen divided by all of the possible times or choices that could have happened. All right? So on this particular circumstance, okay, I'm looking for sunny days, right? Because that's what we wanted to happen. What was the probability that the day in November was sunny? But I need all of the days in November as being in the denominator, because that's all of the ones that were available to me. But I'm really only interested in the sunny days. So how many days were actually sunny? Well, we have to subtract the ones where we had rain and snow. So if 8 plus 3 makes 11, 30 take away 11 leaves me with 19. So that's how they got these numbers. They just took away the other days that weren't sunny. And when you put this in the calculator, 19 divided by 30, always work your fraction from the top down, please, always. You would get like a 0.63 repeating, and we want percent, so we're just going to scoot it 2 places, and so that's how they got the 63.3%. That was experimental, because the days of the month did occur, so it was something that really did happen. It's not just what I think will happen. It's what really did happen, so it's experimental. Okay? So now, do you have any questions on that? Seem pretty okay? Yes, no, maybe? Yeah? Okay. All right, let's look at example 2. Now we're talking about a football team, and we're going to compare experimental to theoretical. All right? So this football team noticed that 9 times out of the last 20 coin tosses, I said that coin toss. I said it right this time. I said it wrong. Coin tosses, okay, have been, let's see, would receive the ball. Who would receive the ball first? Resulted in tails. So what is the experimental probability of the coin landing on tails? All right, So what am I interested in? Tails. So I want the number of tails out of how many tosses? 20. And how many times did they say it landed on tails? 9. So I'm going to take 9 and divide it by the 20. So throw that into your calculator. 0.45, okay, which turns into approximately 45%, right? Now I want you to think about this for a second. If they're tossing a coin, what's the probability of getting a head or a tail? It's 50-50, right? So theoretically, this answer should have been 50%. Maybe that's it. Maybe if they did 22 tosses, they might have gotten there. But it still wouldn't have turned out to be 50% because of the way we divide our fractions and everything. So, but would you agree that 50% probability in theory is pretty close to 45% in reality? Yeah, so those were very evenly matched, weren't they? And the theoretical and the experimental were almost the same. So they were pretty honest. But suppose you have a dice coming into class and you're going to test it to see if it's a legitimate good dice or whether it's a loaded dice. Do you know what a loaded dice is? One that's weighted slightly different, so it's not going to roll as well or as even as it should. Okay. Cheaters at Bunko like to use weighted dice. I'm just kidding. Bunko's fun to play if you've never played it. Yeah, it's fun. It's an old people game. Yeah, it's fun. But it is fun though, all right? You roll dice. Kind of like Yahtzee. Yahtzee for old people. Okay. So in this math class, they brought a dice in and they rolled it 100 times. Okay? So how many sides are on a dice? 6. And on each side you have a different number. Number 1, 2, 3, 4, 5, and 6. Every time they rolled one of the numbers, they put a little tally mark, and the table to the right here shows how many times they got each of the numbers. So the number 1 showed up 6 times. The number 2 showed up 15 times. 3 was 4. The 4 showed up 13 times. The 5 showed up 15 times. But the 6 showed up 47 times. Something doesn't seem quite right with that. But we'll see. Okay. So let's figure out, they may have cheated. So let's find out what the probability of rolling a 6 is, just to see what accurate probability would be to begin with. So if there are the numbers 1, 2, 3, 4, 5, and 6 on the dice, and I want to roll a 6, what am I looking at as far as that fraction? I have a 1 out of 6 chance, essentially, of getting the number 6. So put that into your calculator and see what the percentage is. No, not 0.3. The top number divided by the bottom number. 0.16 repeating, so approximately 16 or 17%, right? So that's that probability. Now let's figure out about the experimental probability that they did. We're going to take the numbers that they did. So they're saying they got 47 out of how many rolls did we have? 100. So what we want was the number 6. We got that 47 times out of 100 total tries. Are they close enough to think that it was a fair dice? I don't think so. Somebody brought in a weighted dice. Okay, so is this dice fair? No. Why? The theoretical is not close to experimental. Okay, they need to be close to each other to be kind of legit. So you kind of getting the hang of it so far? All right, flip it over. Now we're going to talk about how you could make experiments, which they call simulations, when you're given problems. And that's what's going to happen to you today. I think there's about 6 or 7 problems that you actually have to create the experiment. And because I don't have 32 spinners that I can share, 35 spinners that we can use, and I don't have a, what is that, the bingo, the lottery kind of changer-upper thing where you draw something in, we're going to use a number generator on the computer to do that. And I'll help you figure that out here in a few minutes. But let's try to get an idea of how to set up an experiment to start with, because that's half the battle. Okay, so Pete gets a hit. He gets 84 of his last 252 at-bats. He does well. He gets a hit. So 84 out of 252 is the probability of him getting a hit. And this is how you can write the probability. P stands for the probability, and then whatever you're looking for goes in the parentheses. Okay? So the probability of getting a hit was 84 out of 252. Okay? Design a simulation that can be used to estimate the probability that Pete's going to get a hit at his next bat. So, yeah, he's not doing too bad. It's about a 33%, somewhere in there. But we need to figure out how to create an experiment that would work for this. Okay? So you're going to be using, I don't have spinners, I don't have any of that, so I'm going to kind of explain to you how you would put it into the number simulator. So on the number simulator, they're going to ask you how many times you want to try some experiment. Okay? And you can change it to whatever you want. And they're also going to ask you what numbers you would like to use. So you get to choose that as well. So ideally, they're saying they took this fraction and they simplified it down to 2 out of 6, which would be good. Okay? So what this would mean is what? 2 hits, the number 2 would be good, right? 2 would be good. How many would then be bad? Out of 6 tries, 2 tries were good, 4 tries are going to be bad. So for me to figure out this experimental probability, what I'm going to do in the number generator is go, okay, I have a total in the denominator of 6. That means I need to use the numbers 1 through 6 because there were 6 total opportunities. So you're going to put in the numbers 1 through 6 into the generator. It's going to say, how many numbers do you want to use? You would say 6. Then you have to make some choices, and you have to define your choices. And you're going to say, okay, if it generates the number 1 or the number 2, I'm going to say that that's a hit, and that counts as a good. If it generates the numbers 3, 4, 5, or 6, I am not going to count them because they were the bad. They don't count. They didn't count as a hit. So when you plunk this into the generator, and maybe we want to do it 20 times. Maybe you want to do it 50 times. It's up to you how many times you do it. But on this particular circumstance, notice they had a pretty good number of times here out of 252 times. If they're using a lot of times in your original problem, I would try to do a few times big, a little bit bigger number for that. So maybe I might use 30 or 40 as the number of times I would try this experiment in the generator. I'm going to see if I can pull that up so you can see it here. And see if it's still open so you can see what it's going to look like. Oh good, it's still here. Okay, so this is where I'm going to have you go here in a minute, and I'll leave this up. This is a pretty good one because it gives you it shows the numbers right away. You don't have to click it 50 times to do 50 tries. It will do it all at once. Okay, so I want to use, how many numbers did I say I wanted to use? 6 numbers, okay? And I want, oh wait, I want to do about 40 times, sorry. Backspace. Let's say I want to do it about 40 times, 40 experiments, and I need the numbers between 1 and 6. That's what I needed, okay? And you do want it to be sorted because you want to be able to count the numbers 1 and 2, because, right, we said the numbers 1 and 2 would represent him getting a hit. So let's see if we can get this. Oops, that was too far. All right, get random. All right, so it randomly created all of these numbers. That's 40 of those numbers in random, but we have them put them in order so we count them. So how many 1s and 2s do we have there? There's the 3. So 1, 2, 3, 4, 5, 6 1s. 1, 2, 3, 4, 5, 6 2s. So that's a total of what? 12? Out of how many total did we have him pick?
40.
12 out of 40. So we would put that down as our fraction. 12 out of 40. Let me get out of here so you can go back to the page again. So we would say, okay, he's gotten 12 out of 40. If we put that in the calculator, what does that turn into? What is it? Oh, really? Does it really? It does, doesn't it? 30%. Isn't that pretty close to what they guesstimated here to begin with? Nice, because 1/3, right? That's about 30%. That's pretty sweet. Do you see how it worked out well? So our experiment is reflected in this example. So that's what you're going to be doing today on your homework. So, and here we're just going to go down here and go, just some ideas. If you didn't have a number generator, what types of things could you use for these random things? Okay, so guessing. If you had a true-false test, what would be a good tool to use if you had to do an experiment on that? A penny, because it's a coin of some kind, right? Because there's 2 sides on it, a head and a tail. There's 2 types of question choices, a true and a false. So that would be a good example that you could use. Use a coin for this one, because there are 2 choices on a coin, and there were 2 choices on the test. Make sense? Okay. What about someone giving away random 2-liter bottles of pop in 4 different flavors to people as they come through the door? How could you kind of do a guess on what color of pop you're giving these people? Well, a spinner would be good. Dice. Dice has 6 sides, but you could. It'd be a little tough. What about like colored ping pong balls in a bag?
Stevenson?
Yeah.
Can I get Kelsey Keith in the main office for an early dismissal, please?
Yes, you may.
Thank you.
You know, or random poker chips or different colored things in a bag that you could hand out. You could experiment that way, right? Okay. What about this? And this right here, this picnic one is kind of interesting because you will have to do this. This is similar to what we just did. I go to a picnic. There's peanut butter sandwiches, PBs. There's 2 of them. Then there's 2 chickens. Then there's tuna and a turkey. Yeah, everybody has turned their nose up at the tuna. I like tuna. So how many total sandwich choices did I have here? I had 6. What would be a good tool to use? A dice, okay? Now, how would you do this, though? Because I only have 4 types of sandwiches, but there are 6 sides on a dice. No, but that's not a bad idea, but no, yeah. Okay, that works. So we could label the numbers. We would let's let peanut butter, if the number 1 or the number 2 shows up, we're going to call those peanut butters. If the numbers 3 and 4 show up, we'll call those chicken. We'd let the number 5 be a tuna and the number 6 be a turkey. So you could do it with the dice. You just have to assign the specific to it. Does that make sense? All right. So you've got over an hour of class time left. And I'm going to have you get on that number generator and see if you can figure out how to work that thing. Yep.